Hello, welcome. In this video, we're going to expand our rules for antiderivatives so that we can take integrals. But before we do that, let's look at the rules for derivatives from a previous chapter. The reason we want to do that is because when we go to take an integral, remember that what we're doing is finding the antiderivative. So we're basically going in the opposite direction of derivatives. So it's useful for us to go back and think about what were the rules of derivatives for certain functions so that we can start thinking about how to go backwards. So these are all rules for derivatives, not integrals, not antiderivatives. We're going back here. So remember that we had a rule for a derivative that said if you had a function multiplied by a constant, then the derivative d dx of that thing was simply the same thing you would get if you took the derivative of f and then just multiplied by the constant k. So, for example, if you had 8x, you can think of that as 8 times x. So the derivative of x is 1, and then 1 times the 8 in front, the k is the 8, would just give you 8. So of course the derivative of 8x is just 8. So that's a really simple example there. When we took derivatives of sums and differences, we found that the derivative of f plus g was the derivative of f plus the derivative of g. And the same was true for the difference. The power rule told us that the derivative of x to the n could be found by pulling the power out front and reducing the power by 1. We had some special cases. The derivative of a constant was 0. The derivative of the term x was equal to 1. And those are all just based on the application of this rule to special cases. And in a previous video in this section, we've been exploring how to find the antiderivative of this. So instead of subtracting 1, we were doing the opposite, which was adding 1. Instead of multiplying by a power, we were dividing by a power. So keep in mind, we just did the opposite of this rule when we were doing derivatives of things that look like x to the n. And we have 2 more rules of derivatives that we looked at in the past. The derivative d dx of e to the x was itself. So you can start thinking about, if I were going in the opposite direction, what would that look like? And the derivative of the natural log of x was equal to 1 over x. So in the next couple of videos or so, we want to keep all of these rules in mind, because what we're going to be doing in the following few videos is going in the reverse direction. So let's take a look at the rules for antiderivatives now. So let's start with the constant multiple piece, which we saw in a previous video. So this is just restating what we already said. If you have the integral of a function times a constant, k is some fixed constant, then that constant k can come out front of the integral, and then you can just take the derivative of f of x. So you can move k out front if you want or you need to. It's not always required, but sometimes it does help you see or think about what the antiderivative is going to be. For the sum and difference, it's very similar to derivatives. The integral of the sum or the difference of 2 functions, dx, I left off a dx here, would be the same thing as integrating each of those 2 functions separately, and then either adding them or subtracting them depending on what the original problem is. In other words, you can split them up if you need to, and think of them as 2 individual integrals. For the power rule, we already saw this. The integral of x to the n dx is equal to x, then increase the power, divide by that new higher power. N cannot be -1 here. If you think about it, if n is equal to -1, and I add 1 to that, then I'm going to end up with 0 in the denominator, and my antiderivative won't make any sense because we can't divide by 0. So this only works when n is equal to -1, is not equal to -1, every other power or value of n works just fine. For an exponential function, the integral is just itself. We saw that the derivative of e to the x was itself, and so the antiderivative of e to the x is also equal to itself. Now, this is only true when the base is e. It's a special number, remember, it's the natural base. If you have something like a raised to the power of x dx, then the integral will be equal to a to the x divided by the natural log of a. Now, this rule right here, the e to the x rule, is really just a special case of this one here. Because if you think about it, if I applied this rule on the right to this function e to the x, I would get e to the x divided by the natural log of e. But if you pull out your calculator and you compute the natural log of e, it's 1. So e to the x divided by 1 is just e to the x. And then finally, for a natural log, if you do have x to the negative 1 power, so we're back over here to this case that n cannot be negative 1. If it is negative 1, you don't use the power rule. Instead, you use the natural log rule, which says that the integral of 1 over x, which is just a different way of writing x to the negative 1, is equal to the natural log of the absolute value of x. Now, a couple things to notice here. One, remember when we took the derivative of the natural log of x, it was 1 over x. So there's the antiderivative part, right? We're going in the opposite direction. The derivative of natural log was 1 over x. Therefore, when we go in this direction, the integral of 1 over x is the opposite, the natural log of x. The only thing that's different here is this absolute value symbol. It is important. We need to keep that there because you cannot take the natural log of a negative number. Try it on your calculator, you'll see that you have a problem. So we put the absolute value there to make sure that we don't end up with some weird situation where we end up with an error in our calculation. Again, this absolute value is required, so don't leave it off. Back up here, I forgot to mention this special case for the power rule. So if you just have the integral of a constant k, then that's equal to kx. And in a previous video, we actually talked about that. We could test this by saying, let's take the derivative of k times x. The derivative of k times x is just k. So if this were the integral of 5, then the antiderivative would be 5x. And we can check that because the derivative of 5x is equal to 5. Again, remember, you can always check your integration by taking the derivative of whatever it is that you claim to be the antiderivative. When you take the derivative of that, you have to get back what you started with in the original integral. So here are a bunch of rules. We're going to do some examples with these one at a time. So let's take a look at example 5, where we're looking at the integral from 0 to 3 of e to the x minus 4x dx. So we don't have parentheses around e to the x minus 4x, but they're implied. This dx tells me that I'm taking the derivative with respect to x of this entire function that's to the left of the dx symbol. And I have two functions here. I have an e to the x, and I have a negative 4x. So that means I can do these separately from each other, right? When we go and compute this, what we're actually doing is finding the signed area between the graph and the x-axis. This is what the graph looks like here. And between 0 and 3, you can see there's some negative area and some positive area in blue. So you might want to guess, is this going to be a positive or a negative result? Let's find out. When I take the antiderivative of this function, I'm going to do that one piece at a time. The antiderivative of e to the x is itself. Remember, we can check this by taking the derivative. What is the derivative of e to the x? It's e to the x. Check. The antiderivative of negative 4x will keep its negative sign, and because it is 4x to the 1, I can think of this as an x to the n example. So I have to increase the power from 1 to 2, divide by that new power of 2, and keep the 4. So this 4 divided by this 2 just gives me 2x squared. Again, always try to quickly check that you've done this correctly. What is the derivative, going backwards now, of 2x squared? Well, the derivative there is 2 times 2 is 4, x to the 1, and that's what I have here, 4x to the implied 1. The fundamental theorem of calculus tells us to take this entire expression, plug in 3 and 0 in that order, and then subtract them. So when I do that, this left set of parentheses is where I plug in 3. So e to the x becomes e to the 3. Minus 2x squared becomes 2 times 3 squared. When I plug in 0 into the antiderivative, I get e to the 0 minus 2 times 0 squared. And then there's a minus sign in between those two things. So what I get here is e to the 3 minus 2 times 9. 2 times 9 is 18. Here I get e to the 0 is 1 minus 2 times 0. So 1 minus 0 is 1. When I put this into a calculator, I end up with 1.086. It's positive, which tells me over here on the graph that the blue area, which is positive, is a little bit larger in magnitude than the red area, which is negative. So there's more blue area than there is red area. And in fact, how much more? There is this much more area of blue than there is of red. So this is the total signed area for this function between these two values, 0 and 3.